Welcome, everyone, to this explainer. Today, we're demystifying a concept that is literally running the modern world, yet it remains completely invisible to the average person. I'm talking about the OSI model. Created way back in 1984 by the International Organization for Standardization, this 7-layer blueprint is the whole reason different hardware, software, and network tech from across the globe can actually talk to each other. But hey, instead of just staring at a bunch of abstract theory, let's ground this in reality to see exactly how this incredible framework operates under the hood.
Okay, let's dive into this. Imagine Sarah wants to send a photo of her dog to her friend Max over a chat app. It's an action you and I do dozens of times a day, right? She picks the image, hits send on her phone, and literally a second later, Max gets a notification. Honestly, if it takes more than 2 seconds, we get kind of annoyed. But what is actually happening in that tiny window of time? To get that dog photo from Sarah's screen to Max's screen, that file has to go through a highly orchestrated, incredibly complex series of steps. Grounding our explainer in this simple, relatable action is going to show us exactly how the invisible complexity of the OSI model makes all our modern communication possible.
So, here is our game plan for today's journey. First, we'll meet the OSI model. Then, we'll look at preparing the data. Third, we dive into packets, frames, and bits. We'll take a quick detour to compare Layer 2 and Layer 3 hardware. And finally, we'll watch the entire journey reverse.
All right, let's kick things off with Section 1, Meet the OSI Model.
And this brilliantly illustrates the ultimate blueprint governing network communications. You're looking at a visual roadmap of those 7 layers from the sender on the left over to the receiver on the right. When Sarah hits send, her data moves top-down on her device, starting all the way up at Layer 7, the application layer, and cascading down to Layer 1. Then it shoots across the physical network. On Max's device, the whole thing mirrors itself, moving bottom-up from Layer 1 back to Layer 7 so he can actually see the picture. Every single layer here serves a highly specific, isolated function to make sure that data gets exactly where it needs to go.
Now, before we trace Sarah's photo, we kind of need to talk about vocabulary. Networking pros do not just call everything data. That'd be way too confusing. Instead, they use specific terms called protocol data units, or PDUs, to describe the info at each layer. For the top 3 layers, yeah, it's simply called data. But as it moves down, it transforms. At Layer 4, it becomes a segment or a datagram. At Layer 3, it's a packet. Down at Layer 2, it gets encapsulated into a frame. And at Layer 1, it's just raw bits. This isn't just pedantry, folks. Using these PDUs reduces ambiguity. It's absolutely crucial shorthand for professional troubleshooting.
Okay, vocabulary locked in. Let's move right into Section 2, Preparing the Data. This is where Sarah's dog photo begins its descent through the top 3 layers. At Layer 7, the application layer, Sarah's app kicks things off by picking a protocol to send the photo, like HTTP. Then it drops to Layer 6, the presentation layer. This is where the magic happens to ensure the photo will actually be readable by Max's phone, handling vital stuff like file compression so it sends faster and encryption for security. Finally, it hits Layer 5, the session layer. This layer's only job is to establish and maintain an uninterrupted connection between Sarah's app and Max's app while all this data is being prepped for transport. Now that everything is formatted, encrypted, and the session is totally open, we transition to Section 3, Packets, Frames, and Bits. We're moving into the lower layers where the actual heavy lifting happens. Think of it like taking a massive, oversized package and splitting it into smaller, manageable, fully addressed boxes for the mail carrier. Let's look at Layer 4, the transport layer. The formatted data is split into smaller chunks. Segments if we're using TCP, or datagrams if we're using UDP. These chunks get source and destination ports plus sequence numbers so they can be perfectly put back together later. Then it drops to Layer 3, the network layer. This is your routing hub. Layer 3 wraps those segments up into packets, slapping on the source IP address, Sarah's phone, and the destination IP address, Max's phone. This is exactly what allows routers to find the absolute best path across the entire internet.
Next up, those packets hit Layer 2, the data link layer, where they get encapsulated once more into frames. Now, while Layer 3 used IP addresses for global routing, Layer 2 uses MAC addresses for local delivery on the exact same physical network. It also adds a mathematical frame check sequence just to catch any transmission errors. And then we hit rock bottom. Layer 1, the physical layer. All those carefully built frames are converted into a stream of raw binary bits, just ones and zeros. These bits are physically blasted out over a medium, whether that's electrical signals on a copper cable, pulses of light shooting through fiber optics, or radio waves over Wi-Fi and cellular networks.
So the crucial point is, why does this matter? Well, the OSI model isn't just some theoretical software map. It literally dictates the physical hardware running global traffic. Let's pause Sarah's journey briskly for Section 4, Layer 2 versus Layer 3.
Out in the real world, Layer 2 switches and Layer 3 switches do very different things. A Layer 2 switch operates at the data link layer, using MAC addresses to super quickly bridge and redirect packets within a single local network. It's incredibly fast, but honestly, it doesn't care about IP addresses at all. Contrast that with a Layer 3 or multi-layer switch. Operating at the network layer, it has both a MAC address table and an IP routing table. It uses specialized ASIC hardware to perform high-speed IP routing between entirely different networks. Basically, think of a Layer 2 switch as navigating the hallways of a single office building, while a Layer 3 switch is navigating the global highway system connecting Sarah's cell provider to Max's Wi-Fi network.
Now, what's really interesting about this slide is seeing how beautifully these two pieces of hardware integrate in an actual enterprise network topology. You can see the Layer 2 switch at the bottom, handling those lightning-fast local connections directly to the host PCs in a pure Layer 2 domain. But above it, acting as the traffic cop between different departments, is the Layer 3 switch. It's doing the heavy lifting of routing data between different VLANs, like, say, safely getting data from the faculty network over to the students' network.
And this brings us to a super practical, everyday application of the OSI model for IT engineers, picking the right equipment. If you only need to interconnect devices in a local environment, a Layer 2 switch is perfect and way more cost-effective. But the second you need inter-VLAN routing, advanced network security, or fast IP packet switching across different subnets, well, a Layer 3 switch becomes an absolute necessity. Understanding these layers ensures you're deploying the exact right tool for the job.
All right, let's jump back to our narrative arc for Section 5, the journey reverses. Sarah's data was converted into radio waves at Layer 1 and shot over cellular towers. Now those physical bits are finally arriving at the antenna of Max's phone.
Let's move on and see how this builds back up. Watch how incredibly fast this reverses on Max's device. At Layer 1, his phone catches those physical ones and zeros. Layer 2 bundles them into frames and checks for errors. Layer 3 verifies the IP addresses. Layer 4 uses those sequence numbers to piece the segments back together in perfect order. Up to Layer 5 to confirm the session, Layer 6 decrypts and decompresses the file. And boom, Layer 7. Max's chat app gets the fully assembled file, and the picture of Sarah's dog pops up on his screen.
And there you have it, the complete journey of a single message. But what's truly staggering to think about is the scale of this whole shebang. How many billions of times does this exact 7-layer process happen every single second across the global internet? Every text, every streaming video, every financial transaction, they all rely on the structured, invisible complexity of the OSI model to actually function. Next time you send a simple photo, take a second to appreciate the incredible, layered journey that data is about to take. Thanks for exploring the OSI model with me on today's Explainer.